Shall I start, sir?
Sir, please wait. There is an introduction about you. There is a small welcome address. Then we will start, sir.
Okay.
Good morning, everyone. Welcome to the webinar on remote sensing applications in water resource management. Dr. Priyank Praveen Patel, Assistant Professor in Geography, Presidency University, Kolkata. He has completed his PhD on terrain analysis of for sustainable development planning. His research area includes fluvial geomorphology, geotectonics, geoinformatics, analysis of cultural landscapes and artifacts, and the mapping of urban landscapes. It is an honor and privilege for us to have you with us today.
Good
Welcome
morning.
you, sir. I welcome
Thank
all
you.
the participants. I am sure we will be enriched by the webinar. Audio and turn off queries at the end. Welcome you all.
Right. Shall we start?
Yes, sir. Yes, sir.
Okay. Good morning, everyone. This is Priyank from Kolkata. I hope all of you are well. I will try to show you some aspects of water resource management, water resource analysis, fluvial landscape, and such terrain analysis using different remote sensing and terrain data sets. What I will request the organizers is that my internet connection is a little bit weak at times. So if for any reason I get disconnected, please give me a call and I will reconnect. So I'll be able to understand what is going on as I'm sharing my screen. So what I'll do is the field of watershed management and let's say basically water resource analysis, river basin and terrain analysis is very vast, especially using the multitude of remote sensing data sources that have arisen over the last 50 to 60 years, right? But I cannot show you everything, but I will try and give you a flavor of the kinds of work that are done throughout the world and some of the notable research activities that are currently going on. And so then you can choose aspects of it related to your work. We will have a question answer session at the end. And I'm always open to questions during the middle of the lecture also, if you need some clarification about what is going on, right? And I hope you understand it. And I look forward to working with all of you, collaborating in the future as and when that arises. So what I'll start with is I'll start sharing my screen and we'll begin. Right. So this can be seen. So I will start with this. This is the topic that we are basically talking about. Remote sensing for water resources management. I think it can be seen. Yes.
Yes, sir. Yes, sir.
Okay, thank you. So the reason why I want to start with this instead of a PowerPoint presentation, I'll go to PowerPoint presentations, a number of them later on, show you some of the work that we have done in my university, as well as research done by other very notable people around the world. But I'll start with this because I think if you are looking into remote sensing for water resources management, this is one paper that you should be reading. You start from here, right? Everybody starts from a certain base. So satellite remote sensing for water resources management, especially in data poor regions. Now, the issue that we have in India is we are a very large country. We have all manner of river systems and terrain conditions that can exist. But a lot of the data for our country is restricted, especially in the northern half of the country. Because of the presence of international river basins, a lot of the data is restricted. So we are basically data poor. Along with that, even in the other parts of the country, sometimes you want river gauges at very frequent intervals. You want groundwater sampling at very frequent intervals. That data sets is not there. Or you only have the most recent data set. You do not have a long-term 30, 40 historical data set, 30, 40-year-old historical data set. So we are what you can call a data poor region. And so remote sensing and GIS techniques allied with it becomes very, very important, especially for us, because we need to leverage this technology and technique and try and see what we can extract, right? So I want you to go through this paper. I will send the whatever papers and other resources I'm showing you. I'll send most of it along after the end of the lecture, so you can go through it. So this is a AGU publication in a very esteemed journal called Water Resources Research. I'm sure many of you have read this journal. And so what I want to do is show you some of the tables that are there in this. So what are the various, WRM is water resource management. So what are the various water resource management decisions that we seek to do based on GIS and remote sensing networks? What are the traditional data that we use, and what are the remote sensing data that we now have that we can utilize for this purpose? So what are the basic things that we do in water resource management? Number one is, I am from geography. My work is with geography. So one of the main themes that we look at is the interactions between human beings and the environment, right? The human nature relationships, the nature of those relationships, the processes that are there. And we basically consider that this human nature relationship is of two types. Our relation with nature is of two types. Number one is, what are the resources that we can get from nature, right? What are the resources or economic benefits that we can get from nature? And the second one is, how do we protect ourselves from different aspects of nature, right? So that means from various geohazards or disaster events. So human relation with the natural landscape is basically of two types. What are the economic benefits and resources that we can derive? And what are the ways in which we can protect ourselves from the inclement elements that are there in the natural landscape, right? So what are the things that we are looking at in water resource management decision-making processes? One is design of flood control. Then design of hydropower systems, design of irrigation systems, wastewater management, okay, proper water supply systems, and very important transboundary water agreements. So these are the things that we are looking at. So what do we need for these things? The data that we need is rain gauge networks, stream gauge networks, the amount of snow that is there, the snow budget, the annual snow budget of each year, very good groundwater mapping networks, and we need long-term data for this. Right? Then what are the other things required for disaster management? Say crop monitoring, drought hazard assessment, right? Early warning for floods. Then water health related monitoring, that is water quality mapping, water quality monitoring, those things. And something very important that has come up is ecosystem services or ecosystem management, for ponds and rivers and these areas. Right? So these are the kind of different data sets that we need. Now, traditionally, all these data sets are not going to be available because we are, as I said, a data sparse country, a data sparse region. So what can we do for leveraging remote sensing and large big data sets, GIS data sets? So what we have had in the last 20 to 30 years, with the advent of multiple number of different satellites and sensors that have gone up, we have been able to create such databases. Right? So this is the daily precipitation record that we have for different parts. In this paper, they are looking at South America, but you will have this for different parts of the world. Then GRDC is the runoff that you have from different river basins, right? So I'll just proceed. So these are the kind of now data sets that we have for remote sensing and GIS-based models. We have precipitation, we require precipitation data. We require ET. ET is evapotranspiration and potential evapotranspiration data. We require stream flow data, water level gauging and mapping data, soil moisture data, snow and ice data, groundwater data, and water quality data. The reason I am showing you these 8 aspects is each of these 8 aspects can be today mapped, imaged, and extracted using different remote sensing data sets and indices generated from those remote sensing data sets, right? So let me just show you some of the data sets that are there, or some names of some of the data sets that are there. For example, if you look at the precipitation data sets, precipitation remote sensing data sets that are there, this is you have the TRMM, so that is number 1. Then you have Persian, that is available from the year 2000 to present. Then CMorph, GS Map, Chirps, right? Chirps is very good because you get long-term data from 1979 to present, and this is a daily precipitation data set, and the extent is 0.5 degrees, right? So quite good. 30 minutes interval data set, so quite a very good data set. And these are the various papers that refer to these data sets. I'll send along this paper. You can then go to these websites, you can download these data sets yourself, and you can learn how to analyze them. I will not be able to cover all of it in a 2-hour lecture, but I want to give you some knowledge that these are the data sets that are available, because the whole point of you attending this webinar is not just to know the theoretical basis, but to do some work yourselves, right? So you can look at, these are the precipitation data sets. Then something very important, we have land surface temperature data sets. And so land surface temperature, you can say that, okay, that is usually done for urban areas, but we also need it for water bodies. So one of the reasons why we do LST, land surface temperature, for water bodies is it helps us to estimate the evapotranspiration that is going on, right? The hotter the ground surface, the more evaporation will occur from it. Along with that, there are legal ramifications. For example, say I have a green bench in the Supreme Court, and there are strict rules about the kind of water pollution that can be done by an industrial unit, right? For example, they cannot release very hot water or hot effluents from a plant into the nearby ponds or rivers, right? Now, if a industry is polluting, for example, if they are discharging dirty water into a river, that you can see and detect, okay, because the water will be dark color, it will be black in color, and such aspects. But what if they are releasing very hot water, clear but very hot water into a river? How will you notice that? You cannot, because visibly that is not possible to be detected. But there are LST or temperature data sets become important. Why? Because if you do a temperature mapping of the river, and if you see that some parts of the river are significantly hotter than the other parts, and these are situated beside your urban areas or beside your industrial plants, then those industrial plants are at fault for releasing the hot water into this, rivers and their ecosystems, right? So this is one way in which land surface temperature becomes very, very important. Then these are the data sets that from which we can derive LST. One is Landsat, long-term data sets we can use for it. AVHRR, Advanced Very High Resolution Radiometer. This is launched by NOAA, National Ocean and Atmospheric Administration in the US. The problem with this data set is it is coarser resolution, 1 kilometer, but it's daily. So if you're looking at large regional landscapes, a state level analysis or entire, say, subcontinent level analysis, then this is a very, very good data set. Aster is very good. Aster gives you a 90-meter LST data sets. This is available from the year 2000 onwards. And then we have MODIS and VIRS, and today we are having Sentinel data set that is coming up, right? The good thing about the Sentinel data set is its temporal resolution is very low. So you can really track the land surface temperature changes very, very nicely, right? So there are some ready-made ET products available that you can download, because a lot of agencies around the world, they have taken these data sets and they have made ready-made data products, and you can directly download them and use them for your research and work. I'll show you some of the data sets going on. I'll show you some of the websites later on. Then there is the JPL website where you can obtain other such data sets. Then we have very important soil moisture. And this soil moisture is a very required parameter for drought mapping. It is very required for your groundwater availability, crop health assessment. So this is another data set that is there. SMAP. SMAP is used a lot because you get it at quite low spatial resolutions, and you have a very good temporal resolution for it also. So SMAP, root zone soil moisture, these are some of the data sets that are used. Sentinel-1 SAR data is also available for this purpose. Then the next one we have is surface water height and extent. Now, why do we need surface water height and extent? Where do we need? For coastal areas, for large reservoirs, for large rivers, so and lakes also. So surface water data sets are available, and so you can use this to gauge the effects of storms, the cyclone effects, the height of tides, height of tidal surges and tidal bores. So surface water height extents can be ascertained from these different data sets, right? And then very important, because part of our country, the northern part, has a lot of snow cover, and there is a lot of work going on regarding the snow balance in the Himalayas, because how global warming and climate change is affecting this. So these are some of the data sets which look at track snow balance, snow budgets in the across the world, and this is something you can use also. Then a very, very important and new data set that has come up in the last 2 decades is called the GRACE data. GRACE, or then you have the GRACE FO data. So what is the GRACE data? It tracks the gravity anomalies on the Earth's surface, and then it looks at groundwater fluctuations. And there was a very good paper that came out in Nature a couple of years ago, which talked about how using GRACE data, which talked about something called the food, water, energy nexus. And this is becoming very, very important, because we are looking at water resource management, right? For what purpose? We are wanting to manage water resources for our utilization. How do we mainly use water resources? For crop, that is for food, for commercial crops, food crops, and for utilizations in our factories and homes. So for utilization in our factories and homes, the other important thing is the energy requirement, right? The electricity availability. So what the paper did, and I'll share the paper with you, is it looked at something called the food water energy nexus. What is the energy development that has taken place across northern India? As a result of this electricity development, what are the tube wells that have been put into operation? What are the water extraction methods that have been put into operation? And as a result of these water extraction methods, how much groundwater depletion has occurred throughout the northern belt of India, right from Punjab to West Bengal? Right. So this was a very, very seminal paper. And if you are using GRACE data, you can do more such work yourself. And then, of course, vegetation mapping. Now, you can say that, okay, in a water resources management webinar, why are you talking about vegetation mapping? The reason is that today, not only are we looking at the physical state of a river, but we are also looking at the, I would say, the river health or the aquatic ecosystem assessment, right? This becomes very, very important, because as long as a river stays healthy, as long as river restoration schemes are working, we will continue to get the benefits that we can obtain from a pond or from an aquatic ecosystem. As soon as the river or the pond dies, we lose the entire ecosystem services and benefits, and and its monetary value that we would otherwise get from this ecosystem, right? So these are some of the main sectors of water resource assessment using remote sensing and GIS datasets that are there. So these are some examples of the datasets: CMORPH, TMAP, Persian, right? And you can explore these websites. You can go to these datasets. You can explore these websites yourself, and please have a look at it. So these are the LST flux. These are the heat flux that can be mapped, right? So if any of you are doing such work or interested in doing such work, I'll be more than happy to collaborate and learn and work together, right? So these are the main areas of water resource management that we are looking at using remote sensing. So what are the main themes that I talked about? Number one was precipitation assessment. Then water surface temperature, land surface temperature assessment, evapotranspiration assessment. So this basically then becomes water budget analysis, right? Then we look into snow budget analysis, then soil moisture assessment, surface water height, that is wave height assessment, groundwater fluctuation assessment, and vegetation health and mapping. So using remote sensing datasets, these are the different aspects that we look at using the various remote sensing datasets that are there, right? So this is another paper that was brought out by the Indian Institute of Science in Bangalore and IISc Bangalore. And so they list the different aspects of water resource management that can be done using remote sensing datasets. So see, these are the three main points. The aspects that I was talking about, they have condensed into three main points: water resource mapping, estimate, that is, what are the water repositories that are there, what are the water reserves that are there, both surface water reserves as well I'll show you the different algorithms and other techniques that can be used for obtaining these kind of aspects, right? If there are any questions so far, I can take any questions. Okay, fine. If there are no questions, I'll continue. Then this is, so now starting to focus on India. So this is the main aspects that we look at when we talk about watershed management in India. So let me just make it larger, this. So these are the various aspects that we talk about when we look at watershed or water resources management in India or across the world, but mostly in India. These are the main issues that we focus on. So land development using moisture conservation. So for example, if I have to modify a slope and conserve water, and so so where does remote sensing come inside it? I can use remote sensing datasets to track the amount of soil moisture changes that is occurring in the landscape. So where there was a steep hill and there was a lot of runoff taking place across the landscape and was losing the moisture content. Now, if I re-terrace the field, if I re-terrace the hill slope, and if I start to store the water in the small segments of the hill slope, how much is the soil moisture being augmented? Okay, this is one kind. Then development of small water harvesting structures, check dams, recharge zones. And I'll look at groundwater recharge and check dam construction potentiality using remote sensing data sets, right? So the government of India and NRSC, they have certain guidelines. Central Water Commission, Central Groundwater Board, they have certain guidelines, what kind of remote sensing data to use, which are the sites that you should track to implement your check dams and other ponds. So I'll show you some of those examples. Then afforestation assessment, drinking water supply assessment, these are things that can be done using GIS datasets, right? So these are some of the main aspects. And so then focusing more on India, this is a presentation that I just want to show you briefly. It was prepared by Professor Krishnamurthy from ISRO. And I thought that it is best to show you the presentations directly by the experts. I'll share these with you if required, right? So let me just show you some of the aspects that Dr. Murthy was talking about. The reason why we are looking at water resource management is this, that as a country, we are growing in terms of population. So we need to increase our food grain resources, right? We need a lot of technological input towards that. We need to increase our water resources and our food resources, food availability that is there, right? And so what ISRO has done, NRSC and ISRO have done, they have created very, very detailed water databases or groundwater, surface water databases for different parts of India. For example, Maharashtra, okay, different district level. So what are the data sets that they are using? Rainfall maps, and then they are using different other terrain data sets and other such land use, land cover maps, and they are making, let me just show you some of the maps that are there. Yeah, so these are the parameters that they are using. Watershed size, shape, physiography, drainage development, geology, soil, land use, groundwater potential. And so these are the water resource aspects that they are looking at. The runoff, the sedimentation, recharge and irrigation aspects, right? And so these are some of the in-house softwares that they have developed. Most of these software modules will be available from the NRSC website. You can download them. I'll just show you these very briefly, okay? And you will be able to download this and use this. Also, what NRSC and CWC have done, and you can see this at the India RIS website, I'll show you that website, is they have divided the entire country into micro watersheds, both for surface water assessment as well as for groundwater assessment. And so each region has been coded. Within a region, you have a basin, catchment, sub-catchment, and right up to micro watershed. And for each micro watershed, they have made detailed plans, right? And so these are the custom-made softwares that they have used, mapping of drains, mapping of different stream networks, updation of watershed boundaries. And so these are some of the works that they have done in this domain. So these are some of the software modules developed by ISRO. Odrala, that is for drainage labeling. Then they have developed something called water geomorphics, that is for watershed selection and mapping, right? And if you go to the ISRO website, you will see a whole range of such different tools that are available. The codes are usually available. You can download them and you can utilize them for your work, right? Some of them are in-house. They are not available to everyone. But if you can contact them, maybe you can work with them, then you can use these tools that are there. Okay, now the same works we can do utilizing commercial softwares that are there or free data sets that are there. And now I'll try and show you some of those examples, right? So I hope everything is going clear so far. So I'll start off with terrain data sets. Let me just start a presentation. I'll start off with different terrain data sets that are there and how we utilize terrain data sets for watershed mapping and such utilization. So I'll just begin this. Right. So the reason why we have gone into remote sensing data sets, right? And the reason why we have gone into digital elevation model or DEM data sets is this. Now we have topo sheets available for the country, but topo sheets do not show you the entire extent of water resources that is there. Why? Because your topo sheets are usually at 1:50,000 scale or 1:250,000 or 25,000 scale. You cannot I show all the river networks or all the ponds that are there from such coarser or medium resolution data sets, right? So some of these, so for example, this is a river that starts in a topo sheet, but suddenly it vanishes. Is this a new river or is the old river continuing? We don't know. The map does not tell us. Then sometimes you have topo sheets of two different contour intervals. One side is a 10-meter contour interval map, the other side is a 20-meter contour interval map. So you lose information as you move from one map to the other. Then if you're saying that, okay, can I use high resolution Google Earth data? You can. But see, this is a stream network that is there in the Google Earth data. Now, people have done irrigation, people have done cultivation across the stream bed. So you don't really know where the channel is anymore. Where do you want to digitize the channel presently? So there are some problems using high resolution data sets or topo sheets that are there. So instead what we go into is we start using terrain data, that is 3D data sets. And these 3D data sets or DEM digital elevation models are prepared using 3 different methods. One is you are using ground surveying, where you are taking a theodolite or a total station or a DGPS, and you are mapping the terrain in detail. Aerial surveys through aerial photographs. I'm sure many of us have used aerial photographs. Then something very, very new and some very, very important that has come up is LiDAR. Light detection and ranging, where you bounce off light beams of the Earth's surface and you create a very, very detailed, beautiful 3D data set. And that is used for a lot of a range of applications today. The importance of LiDAR data sets is also is that it is ground penetrating. And so you can actually remove the top cover of trees and you can look at the bottom topography that is there. You can even penetrate the, if you're using SAR waves, you can even penetrate the ground to a certain depth, say 30 centimeter or 1 meter, and you can look at the subsurface geological formations or subsurface geomorphic and river channel formations. And this becomes important in water resource analysis. Why? Because you can use this for detecting potential aquifers that are there, to detect potential water resource storage areas or recharge areas that are there. And then satellite surveying, for example, radar data or stereo band data. These data sets today are available, right? So when you're creating a terrain data sets or using a certain terrain data sets, the things you must keep in mind is what is the roughness of the terrain. That is, what kind of resolution should you use, what kind of DEM you should use. If your terrain is very flat, you can use a coarse resolution DEM. You can use large pixel size DEMs. But if your terrain is very rough, that is lots of ups and downs in the terrain, the smaller is the size of the pixel, the better resolution data you will have, right? Then what kind of interpolation algorithms you are using, because different interpolation algorithms, for example, nearest neighbor analysis or cubic convolution, so these will give you different outputs, right? Kriging, TIN interpolation, they will give you different outputs. So you have to be very careful about the interpolation algorithm that you are using. Then the vertical resolution. Usually people only talk about horizontal resolution, but for a DEM, vertical resolution is also important. So vertical resolution here means the vertical accuracy. How accurate is the terrain data set that you are using? For example, everybody uses SRTM, Shuttle Radar Topographic Mission data set. Now that is a 30-meter horizontal resolution data set, but its vertical accuracy is plus minus 5 meters. So the height that it is saying of a particular spot, it can be plus 5 meters or minus 5 meters. Now in a place like the Himalayas or the Western Ghats, it is not so much of a problem because you have high rugged topography. But imagine that you are mapping the Kaveri Delta, or you are mapping a coastal belt, or you are mapping the Sundarbans, the Ganga Delta. There a plus minus 5 meter is a huge difference. So SRTM may not be always readily applicable for this purpose in very flat terrain datasets. You may need to go for much higher resolution datasets for these purposes. All right. So what the other thing that we can do from DEM is, so what is a DEM? If I go into this briefly, you may know this is, it's a regular gridded matrix. So the entire world is broken up into this kind of grids. And for each grid, you have a certain terrain value. You have a certain elevation value. And using these elevation values, we can then create different aspects or the geomorphology of the area. For example, if all the pixels have the same elevation almost, then it's a flat area, plain. If the middle pixel row is lower elevation, then it becomes a river channel. If the middle pixel has higher elevation, then it becomes a ridge. Okay. If the middle pixel, the central pixel has the highest elevation, then it becomes a peak. If it is the lowest elevation, then it becomes a depression, right? Or a pond could be. So these are the kind of data sets that, these are the kind of automatic detection of topographic features that can be done using DEMs. And so the importance here is when we are doing water resource analysis, one of the very important things is that we need to understand the nature of the topography. So using the DEM datasets, we can directly map the topographical features, and then we can utilize that for detecting water reservoirs or recharge points and other such purposes, right? So if you, a lot of you must have used DEMs, so they become easy to utilize for ascertaining terrain aspects. You can directly extract surface profiles from them, right? So maybe representative profiles or superimpose surface profiles. You can show beautiful things in 3 dimensions, folds and faults and other features. So you can do a terrain classification, as I was saying. Then the very important thing that can be done using DEMs is called watershed delineation and potential flow line extraction. So what is this? Imagine if I am dropping, if a drop of water is falling on a landscape. For example, if a drop of water falls on this cell over here, called 67 meters height. So where will that water droplet go? It is most likely to go to the number 44, because the height difference between these 2 cells is the maximum. So if I draw an arrow showing which way the water is flowing, then from 44, it will most likely go to 22, then 16, then 11. So if I join these arrows, I get a small stream that starts to come out of the landscape. So using this method, I can join the different arrows and I can extract the water, I can extract the drainage network that is there. And this drainage network, then I do not have to trace or digitize from a topo sheet. I can use directly for my different water resource assessments and water map or stream network morphometry map preparation. Right. So this is a very, very important technique. Now the technique that I showed you is called the D8 method. Why is it called the D8 method? Because surrounding the central cell, you have 8 different cells. Now the water is being directed to only one cell. So that is called the direction 8, D8 method, right? Now you can say that, is this method absolutely correct? Should all the water go into a single cell? So from 67, should all the water go into just 44? Can some of it also not go to 53 or 56? Because these are also lower elevations, correct? There are other algorithms for that. Now, the most likely we are going to use, most likely you are using something called ArcGIS, right? For your different remote sensing data analysis. ArcGIS only has the D8 algorithm that is inbuilt. It does not have the other algorithms or the other more complex algorithms that can be used for watershed streamline assessment. I will show you some softwares that have those kind of algorithms, because they are in some cases better than the usual algorithms that you get in ArcGIS or such software suites. Okay, so we can characterize river channel networks. We can do stream hierarchy. We can extract contours directly from DEMs. That becomes important for looking at the terrain landscape. Then we can understand the slopes of the streams. This becomes important because if you want to put a check dam or if you want to create a hydel power project, what are the stream gradients? That becomes very important for analysis first, right? Then also analysis of stream gradients is important to understand the travel time of the water. The greater is the stream surface slope, the faster will a volume of water move downstream. So channel gradient extraction is a very important exercise in water resource or water hazard assessment. Then we can create nice 3Ds. We can superimpose geological maps on 3Ds. I'm sure you have done all these things before. We can extract nice surface profiles, serial profiles of a drainage basin and see the river valley structure, right? Now, the thing that I touched on earlier was the resolution of the DEMs, right? What are the resolutions of a DEM and how they extract these kind of data sets that we can obtain from them? So what kind of data sets? The basin outline, the stream network outline. So the resolution is a very, very important thing, right? So we did a paper on this and I'll share the paper with you. We did a paper on this in a mountain river basin. We took a mountain river basin because in the flat area, the ambiguity of the drainage structure is a lot more. In the mountain river basin, it is much more, steady. It is much more accurate. So we extracted the drainage basin from a 90-meter SRTM DEM and see the same network if you extract from a 30-meter Aster DEM. What is the huge amount of change? Obviously, the 30-meter data set will give you more detail than the 90-meter data set. This is 90-meter data. This is 30-meter data, right? Then this is a Kato DEM 30-meter data. The Kato DEM that is available from Bhuvan website. I'll show you the website if you have not seen it earlier also. Then this is the 1:250,000 topo sheet contour and the network derived from it. Same 1:50,000 topo sheet which is what we digitized, and the drainage network derived from it. Okay, so, and different basins derived from the different data sets that we have, from 90-meter DEM, 30-meter DEM, 1:50,000 scale topo sheet, 1:250,000 scale topo sheet. The reason why I am showing you this is, any research that you are undertaking, you need to justify first the resolution of the data sets that you are using. This is very, very crucial. Whether it is image data sets, whether it is digital elevation model data sets, you need to justify the resolution you are using. You need to gauge, you need to judge whether the resolution of the data sets that you are using is appropriate for your kind of work, right? And so therefore, if somebody is doing a PhD, or if somebody is guiding a PhD, I would recommend that you tell your student that take different data sets that are available, run the entire exercise on all the data sets, see which one matches reality the best according to your requirements, and then take that. Because a good journal or a good, a good adjudicator will ask for this kind of information. What was the impact, or what was the effect of the resolution of the data on the results that you derive from it? This is very, very important. And so we did, we took a GPS tracks also, and we tried and see which data set matched best with the GPS track. And so we ascertained which was the best DEM, which was not the very good DEM data set. Okay, so say we all do morphometric mapping, relative relief, elevation mapping. This is the elevation map derived from the different data sets that I was showing you. It changes. Now that's why which kind of data you are using becomes very, very crucial. Again, the other data sets that you are using, and we did a difference. We took the Survey of India topo sheet as the base, and we subtracted the other DEM data sets from this. And we saw where it was positive anomaly and where it was a negative anomaly. What were the differences, right? So it really changes a lot. So what we found is the Aster data set 30-meter had the lowest deviations. And so we thought, okay, the Aster data set is something good that can be used. This was done in 2014. Then SRTM 90-meter data set was available. Today you have SRTM 30-meter data set also that is available. All right. But you must be careful. Then there is the JAXA from Japan. They have brought on 30-meter data set. You have the World DEM, that is a 12-meter data set. Then you have Kato DEM for India, that is a 30-meter data set. But you must be careful whether it is a geoidal DEM or whether it is an ellipsoidal DEM. Geoidal DEM will give you the terrain height from the sea level. Ellipsoidal DEM will not give you the terrain height from the sea level. You have to do the ellipsoidal correction to get the height from the sea level. So whenever you are downloading the different DEM data sets, today we have the ALOS Pulsar, that is a resampled 12.5-meter DEM, right? It's a resampled data from the SRTM 30-meter data. So when you're using these data sets, please be sure to check whether it's a geoidal DEM, that is referenced from the mean sea level, or whether it is an ellipsoidal DEM, it is not referenced to the mean sea level, but to a local reference ellipsoid. You must do that correction using the, it is called the gravity anomalies that is there, the undulation, gravity undulation data sets that is there. These are available online. If anybody has a question, I'll show you these at the end of the talk, right? But you must do these corrections before you are going for this, okay? Then you must be also careful whether your DEM dataset is a DTM, that is a digital terrain model, or a DSM, digital surface model. A digital surface model will show you the height of the terrain as seen from top. That is the first height. That is the first surface height. Okay, so it will actually record the height of the trees along with the height of the land surface. It will record the height of the buildings along with the height of the ground surface. So it is not showing the actual bare topographic height. The actual bare earth or the bare topographic height is shown by the DTM, the digital terrain model. So for watershed applications, the DTM dataset, digital terrain model dataset, is far more accurate and far more applicable than a DSM dataset. But DTM datasets are much, much more expensive. DTM datasets are not really available for free, at least in our country, right? In other parts of the world, you will have LiDAR DTM and high resolution aerial DTM datasets that are available for free, but not in India as at present. So we end up using SRTM and Aster or ALOS Pulsar, which are all DSM datasets. So we adjust with that error, right? We consider that error to not be there. So, but this is something that you must be aware of while you are doing a research. Okay, then let me show you what can be done using very high resolution DEM datasets or image datasets. So we did some gully mapping and soil loss modeling because that is also a very important part of watershed analysis. right? What kind of soil loss is happening from different parts of a watershed, because there you need to put your check dams and you need to conserve the water and you need to conserve the soil. So we did some mapping in a small part of West Bengal in a gully terrain, and we used very, very high resolution data. You can see the data resolutions, 50 centimeter, 31 centimeter image data sets, and a very, very high resolution 2-meter DTM, that is bare earth model data set. And this is the gully system that you can see. We could extract 1-meter contours from it. This is the terrain features that is there. And using these techniques, what we now have is, you can tell a software to find out surface curvature of the topography. And surface curvature of the topography is another very important terrain parameter. What is it? It shows the it shows whether the terrain is convex or whether it is concave. Now, why is this important for water resource analysis? If a terrain is convex, right? So if a terrain is convex, then that means whatever water is falling on it is running off. It is diverging. It is flowing away from that area because it is convex, right? It is round upwards. On the other hand, if it is concave, that means it is round downwards. So whatever water is falling over here, it is concentrating over there. It is accumulating over there, right? So in a convex landscape, what will happen? Water will run away from that place. You will have runoff. You will have sheet wash erosion that will take place. Whereas if there is a concave topography, if there is accumulation of water in that place, then you will have a stream network that will start to flow out that from area, and from that area, from that point, and you will have a river that is originating, a gully that is originating, and you will have soil loss happening from that particular area through river channel incision. So whether a topography is concave or whether it is convex is very, very important. So you get that using curvature analysis. And using this curvature analysis, we can therefore point out automatically the different gully pixels that is there, because they will be the concave pixels. You can overlay them on Google Earth, see whether it is accurate or not. Then you can demarcate the various gully basins. You can find out the total amount of soil loss happening from them. So these kind of works can be done. Then because we use very high resolution image data sets, we could track the gully growth and across time. And because there was a pond that is there, so this is the gully expansion that took place. And because there is a check dam over here, we could see the pond that formed behind the check dam, the water resource that is accumulated behind the check dam. And we could track all the small stream networks draining into that check dam, right? And therefore, we could demarcate these basins. And from those basins, for each of those basins, we could see the soil loss that was happening from each of those basins. So this becomes a very, very important aspect of watershed analysis and mapping, right? Now, this is done using those 2-meter data sets. But today we have a very new technique that has come up. Even when you have very high resolution terrain data sets, the results that I showed you could not be done from SRTM, because SRTM is 30-meter data. So that's why in a very minor topography landscape, you need even higher resolution data, right? So we used 2-meter data sets that we purchased under a project. But sometimes what you need is, you need even minor features that cannot be seen by 2-meter data, or you need features that cannot be seen, from a top-down view of the landscape. So therefore, we have a new technique in remote sensing called structure from motion. And what structure from motion does is, it's like you take a camera and you go across the landscape. And if I show you a video, so see, so this is a camera and you image all around a feature, right? And this is what is done by drones. So UAV based watershed assessment or water resource assessment is a really upcoming field today. So drone based watershed assessment, this is what they do. They use the SFM principle, right? And so what it is done is, the cameras image all around the feature, and then all the different camera angles or views are intersected. And once you intersect all the different camera views, you will get the object feature in between that you are trying to detect. Okay, so let's just give you an example. So you put it into a software, and the software will plot the different positions of the cameras, and it will create the object in between. For example, this is a rock. Okay, and you can see these are the different camera angles and their views that they are showing. This will be automatically plotted. And once you plot this, for example, say, I'll show you some case studies. This is a small gully. Now you can't see this gully in Google Earth, but this is the actual field photograph of the gully. Now we took a lot of photographs. We took around 260 photographs and we processed it in specialized softwares. We use this camera. And once you process it, just like in aerial photograph, or just like you do in artificial intelligence, you do image recognition. So the software will do image recognition, will plot the different photographs, create something called a point cloud, right? And using that point cloud, it will plot the different points that it is recognizing, and it will generate a 3D topography of the landscape. So these images that you are, these models that you are seeing, these are the generated 3D models, right? These are not just images. These are actual 3D models of the landscape. And so let me just show you. You can see this, then this, then you can see this. This is not a photograph. This is the actual 3D model of the rill and gully. You can see the channels where the water will flow through, the soil loss will occur. This is the actual model with the texture, with the grass and the soil color superimposed on top of it, right? And what do we get from this? We can get very high resolution 25 centimeter data sets on which you can do your surface mapping and flow analysis and other such aspects, right? So this is something that is very new that has come up, right? So for example, if you have to map a single rill, so we took some photographs, 500 photographs, and we mapped it and we plotted 8 million points. So by plotting 8 million different points, you generate the entire topography. And so this is the topography that comes, and you can then map the different aspects, and then you can do the analysis that is there, right? So along with this, if you have a field instrument called, those of you who are interested in geology and the impact of geology on water resources, rock formations on water resources, which a lot of civil engineers look into, if you have an instrument called the Schmidt Hammer, this is what the Schmidt Hammer looks like. You can test the rock resistance. So you can plot that, you can make a 3D of the landscape, and you can look at the different rock resistances that are there in different parts. So you can judge soil erosion taking place as a result using this, right? So this is something, this is a data set that, this is a kind of technique that has come up. This is the same, this is the ground-based remote sensing that I showed you, but the same technique is used in drones and in LiDAR mapping. And so what they do is they do structure from motion. They create what are called point clouds, and using these point clouds, they create such 3D topographic layouts, and then those are used to do water resource analysis and create drainage networks and so on, right? So the next thing that I'll show you is related to this. You can do this. So another way of doing this is not strictly remote sensing, but this is related to your flumes. So a lot of civil engineering departments have something called a flume. In my department, we purchased a small flume. And how is that important in fluvial analysis or water resource analysis? It's a small table. We can pack up sediment on the table, right? And then once we let water flow through it, we can simulate the movement of water through the table, and we can then, create a mesh over it. Let me show you a video, because just seeing simple, this presentations may become boring for you. So let me just show you a video. Can my screen be seen so far? Yes.
Yes, sir. Yes, sir.
Okay. So can you see the video?
Yes, sir. Yes.
Okay. Thank you. So I hope it's interesting so far. If there is any problem, please let me know. So this is a flume that we can develop, and you can see the river meander development that is taking place. So if you are a civil engineer who wants to study meander development or erosion taking place along river banks, if you want to see where a dam can be put along a river, so these are models that you can use, right? And once we create such models, and I'll show you the next video, small one that is there. Just a minute. Stop this. Then this one. Right. So this is, say, a delta formation and development. To see how the plume of sediment comes out and forms a delta. Okay. So if these kind of things, once they are formed, then what we do is we can again do the structure from motion. So the reason why I'm talking about structure from motion is it is part of handheld remote sensing. Okay, there is satellite-based remote sensing. Structure from motion is airborne or even handheld remote sensing, where you can use your mobile use your mobile camera, and you can make your own 3D data sets, and so therefore you don't even have to pay anything to anyone, right? So we could make such nice 3D data sets, get cross sections and profiles, create the delta that I showed you. We could make the outflow of those deltas, and we can make some small 3D models from it. Okay, so this is the kind of mapping that can be, or the kind of lab-based work that can be done using this kind of work. Let me show you some of the 3D models that we made here. So this was the original topography, and when the water went through it, this is the resultant 3D topography that happened. This is done using the SFM technique that I just showed you. Okay, so we can look at meander development, bank erosion, river bank erosion, which are the structures and villages that are at risk to this. Okay, so this kind of work can be done. Okay, then if you want to know more about this, these are some of the very good papers that are there. that have come out in very, very esteemed journals. So these are some papers that are there you can look at. Okay, so I'll just stop this one. Then the next one related to is the aspect that I talked about is the flow direction analysis. The most important thing that I told you while using the DEM was what kind of algorithm you are using to extract the river networks, right? So this I showed you just a while back. So this is the typical method. So we have a DEM, we fill the sinks, we fill the data sinks, we do flow direction, flow accumulation, and we extract the water drainage network. But typically what we use, as I told you, is called the D8 network, right? So this is the D8 network. From the center of the water, from the center of the cell, water will go into any one of the 8 cells. It will go into any one of the 8 cells, correct? So this is what I showed you a little bit earlier, and this is the kind of output that you get. But there are other algorithms. For example, multiple neighbor flow algorithms. Now these are called the MFD algorithms, or for one example is the D infinity algorithm. So this kind of algorithm becomes very important where you are looking at mountain peak areas, because imagine rainfall falling on a ridge. It will go on both sides of the ridge. It will not go just one side of the ridge. Imagine rainfall falling on a hill. It will go all around the hill, not just one side of the hill. So their D infinity or the MFD, multiple flow direction algorithms, are much more relevant than just the simple D8 flow algorithm that is present in ArcGIS software, where all the water is put into one side. So what is the result? You are overestimating the water flow on one side and you're underestimating the water flow on the other side. So on one side of the landscape, you are getting a higher amount of rivers than is actual, and on the other side you are getting a deficiency of rivers than what is the real or actual situation. So this is something that you must really keep in mind, and therefore you must explore softwares like Geospatial Whitebox, right? Geospatial Whitebox is a software that allows these MFD algorithms or D8 flow direction algorithms. Those are inbuilt into it, and so you can use those for your work instead of just blindly following the D8 algorithm or technique that is there in ArcGIS or ArcHydro software suites. Okay, so I'll show you an example of it. This we did. We took one SRTM tile, and see, these are the different 6 flow algorithms that I analyzed. And see, for each kind of flow algorithm, the outputs we are getting is very different. Somewhere we are getting stream order 9, somewhere we are getting stream order 8, somewhere we are getting even stream order 7. The number of stream segments in each order, that also is becoming quite different. So you realize the differences that is occurring in the landscape or the kind of data set that you are extracting. That's why it's very important to judge which algorithm also is important in your area of work. Like I told you, when you're advising your student or doing your own research, just as you're telling them that, which just as they have to justify which resolution or data set is applicable for them, if they're using a DEM dataset and extracting river networks, they must also justify which kind of flow algorithm they are using. So there, it is not logical to say that, okay, D8 is used by everyone, so I will just use D8. No, you have to show these statistics and justify ideally, why are you using this particular network? Okay, or why are you using this particular flow algorithm? Okay, so see the changes that occur. We take stream frequency, that is number of streams per unit area. See how the maps change in the different methods. So if your stream frequency is different, that means the number of streams in an area is different, right? And so the water resource estimations that you are going to do, that is going to become absolutely different from each other. That's why this is very important that you have a careful assessment of which flow algorithm you are using, right? So we did this for a topography, and what we saw is that in the flatter areas, that is the green areas, you have a overestimation of river networks, and in the higher areas you have a underestimation of the river networks. Okay, so these are the problems that is there with the D8 flow routing method, that almost 99% of people use, and they do not explore other flow routing algorithms. So please be careful about this aspect, because if you submit your work to a good journal, and they are likely to ask you this question. All right, so this is something that was very relevant, and I thought that you should know about. All right, then so what basically we have been talking about so far is river modeling or fluvial landscape modeling, right? And the two main types of modeling that is done is One is rainfall runoff modeling and one is flood modeling. Okay, and these are very, very specialized branches of study today. So I could just give you a lecture on flood modeling for, say, an entire day. There are so many different aspects of flood modeling that is there. Earlier, we would just use flood imaging. But today we also have different other issues that are there that are doable. Anyhow, so what these models and these data sets, remote sensing data sets, are used for is to create something called a HIS. HIS means Hydrological Information System, right? Where you have a lot of data input, the technological techniques input, and then you have the output preparation and using that for different societal decisions. So this is what is done, right? Data dissemination. We understand different hydrological processes. We do flood forecasting. We do a lot of modeling, and these three things then we utilize and we do some policy and planning and disseminate that, tell that to the general public. All right. Are there any problems going on? Is it fine so far? Hello?
Yes, sir.
It's okay? Okay, fine. So one of the important things that we do is rainfall and stream flow measurement. So what do we do in this is, we look at all the different aspects or all the different components of the hydrological cycle. So this entire hydrological system analysis can be broken into 4 parts, let's say. One is the precipitation analysis. One is the rainfall to runoff analysis. So rainfall to runoff analysis means the amount of incipient precipitation and the amount of resulting rain discharge that occurs in the streams and rivers of that particular area. Now this rainfall runoff analysis is very, very complex. Why? Because this will also involve your evapotranspiration losses. It will involve your surface storage of water. It will involve your groundwater storage of water. It will involve the interaction between the groundwater system and the surface water system. So you're also looking at simultaneously the fluctuation in the groundwater table. So this is the entire component, and different kinds of land use will give you different kinds of runoff. For example, a forested area will give you much less runoff because there'll be much more loss through evapotranspiration and much greater amount of seepage. Whereas an urbanized area, which is concretized, which does not allow infiltration, will give you a higher amount of runoff. So your peak of the hydrograph will be much more higher, right? So that entire landscape analysis becomes ensconced within this rainfall runoff analysis. Then taking ahead this rainfall runoff analysis, so you have the amount of runoff that is occurring in the river. From that amount of runoff, then you are going to decide whether this runoff is adequate for the river or whether the river is not able to, carry this amount of runoff, and therefore the resulting effect is floods. So therefore, from rainfall runoff analysis, we go into flood analysis, or what is called inundation analysis. So along with this, we also do something called E-flow analysis. So E-flow means environmental flow. So the amount of discharge coming into a river, it can be 3 types. It is just optimum. So it just suits the requirements of the river biota and aquatic ecosystem. It can fall below the requirements of the biota and aquatic ecosystem. So there we do the E-flow analysis. What is the minimum amount of discharge required to maintain a healthy aquatic ecosystem? Or the amount of runoff coming into a stream can exceed the amount of water that the river can carry. There it will therefore become the flood analysis, because then the water will come out of the river system and you will have what is called inundation mapping, inundation analysis. I will show you some examples of this going ahead. So then finally, after flood analysis, what we do is something called risk analysis, flood risk analysis, because there you have the policy recommendations. There we do flood insurance mapping. We do what is called flood vulnerability assessment, which homes or which villages are most susceptible to floods occurring in a particular landscape. So this is the kind of mapping that can be done over time. Okay, so this is what I was talking about: runoff mapping, stream flow analysis, and we use something called we use these equations. We use water balance equations that is there. Either we can do discretized model, semi-discretized model, semi-distributed, lumped. So these are some of the terms that you must know. And I'll show you some resources where you can learn these terms if you really want to go into watershed analysis and modeling. Right? Most of you may be doing it already. Right? So I apologize for repeating these aspects. So, and these are the data sets that are available, GRDC. Then, so this is the annual cycle of runoff. So using remote sensing data sets and overlaying them on GIS data sets, we are able to now do this. See, from on the top, you will see the month. The month will come in red. And then you will see the runoff taking place in different parts of the world. See, in July, August, September, the India over here, becomes very dark blue. So that is the when we have our highest amounts of runoff. So we can create very nice annual water regimes using the remote sensing and data sets and GIS domains, right? So for January, July, okay. Then stream flow assessments for different rivers. If you can go to this website and you can get these resources, you can download them, right? They're all free to use. So for different rivers of the world, major rivers in Asia, so all these things can be done. Okay. So this is what all the models will do this. They run the water balance equations. Then there are something called the Saint Venance equations, Manning's equations. They will run all these equations. The SCS method. SCS is the Soil Conservation Service curve number method. This was prepared by the USDA, United States Department of Agriculture, where they showed that what kind of or what proportion of runoff will be likely to take place from what category of land use. So an urban area will have a very high CN value, curve number value. Why? Because more amount of runoff is likely to take place from, or more proportion of falling rainfall is likely to be converted into runoff from an urban concretized area. Whereas in a forest area, the curve number value will be very low because most of the water will be absorbed by the plant roots, or it will infiltrate through the groundwater into the groundwater, or it will be lost through evapotranspiration. So this curve number method, if you want to go, you can search the SCSCN method, Soil Conservation Service curve number method. This is a very popular technique that is used for such analysis. All right. Then water balance equations. These are the kind of equations that are solved in the different softwares. And then we use, the output is a hydrograph, right? And so we, along with this, we can take direct stream measurements. So you can do it by, field personnel, or you can use these kind of methods where you use a chain and, this kind of instruments, current meters, or a new way of remote sensing, that is acoustic Doppler profiles, ADCP. So this acoustic Doppler radar profilers, what they do is you can pull the boat, or the boat is controlled using remote that will go across the river. It will send sound beams, and that will reflect, come back, and you can gauge the flow velocity, you can gauge the sediment concentration, you can gauge the bathymetry of the channel. And this becomes important. You can do this for ponds, you can do this for reservoirs, behind dams, you can do this for rivers also. So this is another domain of remote sensing that is very much applicable for water resources, right? And then we put all of these things, we can do field measurements, then we put all of these things into what is called this
Priyank sir, can you hear my voice?
Right. Hello.
Hello sir.
Hello.
Sir, now you are audible.
Now I'm audible, right? I'll just switch off my camera so that the problem is less on the network. We are having some network problems over here. I'm very sorry.
No issues, sir. No issues.
Okay. So I think you could see up to the hydraulic routing.
Yes, sir.
Flow routing.
Yes.
Yes.
Yes, sir.
Can someone tell me how far did you see the precipitation analysis? Yes.
Participant, kindly answer.
Can anyone let me know? All right. I'll just continue from where I was then.
Okay, sir. Okay.
Right. And right. So what we do is we do this HEC-RAS and HEC flow routing. So I'll show you some of the softwares. So these software modules are there, and you can, without wasting more time, this is the kind of work that you can do. Let me show you some examples. So for example, this is your flood mapping that can take place in HEC-RAS. See, you have a river system, and you have input the various drainage data, and you are running the model, and you can show the inundation that is taking place across the floodplain, right, at different times of the year as the water amount is increasing in the river as it is going down. So this is something that can be done, right? Then what I'll show you is some of the websites that is related to this. So if you go to something called HEC-RAS, if you go to this website, these softwares are made by the US Army, right? Then if you go to that particular website, then HEC-HMS, all these softwares are free, right? And so you can download the softwares. There are tutorial modules that are out there. You can obtain some data. So this is the HMS, right? And then you will see a whole list. One is HEC GeoFDA, that is floodplain. One is for flood insurance. And you can have a lot of different applications. One is for reservoir simulation. So all these things are out there, right? Let me show you a list of such software. So HMS will be for rainfall runoff simulation. Then HEC-RAS will be for flood simulation. Then ListFlood FP is again flood simulation, right? Delft 3D is made by ITC Enschede, that is in Holland, one of the best places in the world for fluvial remote sensing and analysis, right? And so there this is for your morphodynamics, that is sediment mapping and other such studies in the river. Telemap 2D is for levee break analysis. So if you have a river levee, and you are concerned that it can break and flooding can occur in the low-lying areas, you can do that. Then one of the most popular models that is there in the world is SWOT. SWOT is the soil and water analysis tool, right? And if you go to soil and water analysis tool website, right, I'll just go there. If you go to the soil and water analysis tool website, then this is again free, and this is done for climate change analysis, climate change, long-term flow and sediment analysis. Okay, so this kind of change is done. This is the website for SWOT. This is one of the most widely used models across the world. You can go ahead and utilize for this purpose. Then we have WEP. WEP is Water Erosion Prediction Project. So soil loss mapping. Along with USLE. USLE is the Universal Soil Loss Equation. So soil loss mapping and soil water or soil moisture estimation at the field plot scale, right? This can be done using web. Okay, so these are some of the issues that you can do. Then if you go to this website called Hydro Office, let me show you this website. This again contains a lot of free tools and data sets. Now data sets you will get today in India, you will have a lot of data sets. So you will have, for data sets in India, hydrological data sets, you can go to the India RIS website, right? So let it load. And if you go to the Hydro Office website, it will have a list of tools. So this list of tools will allow you to do different 1D plots, 2D plots, recession curves of rivers, base flow analysis and runoff analysis of rivers, right? Then it will allow you to do some reservoir mapping. So in this website, you can look at those kind of tools that are there. Okay, so this is something that is very much applicable. If you can go to the India RIS website, if you can get water data online, surface water data. In surface water data, you'll get river monitoring, reservoirs, all this, rainfall, soil moisture, groundwater data, groundwater quality, all these data sets, now it is available for download and you can utilize for that purpose. Okay, so these are some of the big models that are available. Along with this, everybody uses Google Earth, but along with Google Earth, there is now something called NASA Worldwind, or actually NASA Worldwind is actually older. But if you go to the NASA Worldwind Digital Globe platform, you'll get a lot of hydrological data resources that is there, right? You can just explore this platform along with Google Earth. Okay, so this is something that is available. Apart from this, let me show you, there are a lot of data sets. For example, I was talking about the rainfall data sets that is there. So the TRMM and the rainfall data sets, it is available from this website. Okay, the US repositories. So it is available from those locations. Okay, and also if you have heard of this Google Earth Engine, along with Google Earth, today we have something called the Google Earth Engine. So you can go over here, you can register over here. And once you register over here, what Google Earth Engine allows you is, see, usually how we do remote sensing analysis is we download all the images on our laptops or computers, and then we process them. And that takes a lot of time. It takes a lot of machine resources. In Google Earth Engine, you can just write some simple codes, or the codes are many codes are available for free. If you just write in the codes, if you give the time period, it will automatically analyze the data sets for you and make beautiful animations or give you some outputs, and you can utilize it for directly in your work, the diagram that comes, right? So I'll just show you some small examples of Google Earth Engine your issues that things that can be done using Google Earth Engine. Just a minute. Okay, so specifically for water resource assessment, see, this is the water resource mapping that can be done. See how the inundation is taking place as a result of a dam construction, before dam situation, after dam situation. So you can just do these animations in Google Earth Engine, right, directly. These things can be done, all right? Or as per the season, what is the change in the extent of surface water bodies in a delta? This is a Mississippi Delta. So as per the season, what is the change in the amount nature of surface water bodies within a delta? Okay, this can be done. Or if you want to show river shifting, so what kind of river shifting is occurring as a result of the movement of the meanders. So this kind of animations can be done through Google Earth Engine, and you can use a lot of remote sensing data sets, and you can model this together on the cloud platform, and you can directly obtain these products and utilize this in your research work. Okay, so these are the TRMM data sets. Okay, there are so many other data sets. If you go to the GES disk website, you will see the data collections. And if you search, for example, hydrology, and it will give you a whole range of such data sets that are there, and you can utilize those things for your work. Okay, so there are, see the whole range: groundwater and soil moisture data from GRACE, land model data, energy balance data, right? Then time averaged surface flux data. All these data sets today are available. They are taken by the different kinds of satellites and sensors, and you can directly download this and utilize for your work. So I thought that in my lecture, I'll talk more about these things, the things that you can utilize, because while you're utilizing them, you will learn hands-on, rather than just giving you a dry theory output of, these are the basic principles. All of you are more experienced than me maybe, and you can learn the principles yourselves. But I thought I'll show you the different data sets that are there, which you can utilize for your work. That is much more applicable, right? And so as regards this, so different kinds of models are there. And I will then therefore encourage you very much to have a look at the works of two very important people. One of them is P.P. Majumdar, Professor P.P. Majumdar, IISc Bangalore. He does a lot of watershed modeling and analysis. You can look at his publications. Another is Professor V.P. Singh. Professor V.P. Singh is at Texas A&M University, and he is very widely published in the hydrology and water remote sensing domains. So if you want to look at the different kinds of models that are there, different kinds of abstract stream flow generation techniques, sediment transfer techniques, reservoir analysis that is done, you can go through the writings of Professor V.P. Singh at Texas A&M University. Also, I will suggest you that please look at the resources that have been put online by Professor Idiho. Professor Idiho from this IIT Bombay, Department of Civil Engineering. He makes a lot of good lectures, and these lectures are online, and he talks about watershed modeling, different techniques, right? So in my lecture, I can just give you a flavor of what are the things that are done. You can get much more detailed information from the lectures from these experts and on different aspects. So in his presentations, you will see, say, the different kinds of models that are there, and learn the different kinds of, I'll just show you one particular slide. I'm waiting for that. So different methods, the rational method, then just a minute. Yeah, so what do you mean by lump models? What do you mean by semi-distributed models? What do you mean by distributed models? If you are going into hydrological analysis using remote sensing data sets, you need to understand these kind of models first. Okay, what is a physically distributed models? For example, we mainly solve the Saint-Venant equations developed in 1871, where we look at there's a whole range of differential equations which are used to analyze the flux of water and sediment across the landscape, right? So these equations are solved by the softwares, and these are the different kinds of softwares or different kinds of models that are available to solve these equations, right? So some of them are for surface runoff, some of them are for infiltration analysis, groundwater, evapotranspiration. So all different models are there for different purposes. Okay, so depending on your work, depending on your requirement, you will have to understand which kind of model you want to use, then look in the data sets which you want to use, right? So this is, please read more about this, and please look at the publications of these three gentlemen. You will learn a lot from their research outputs. All right. So this is something that I wanted to stress about. I'll show you some examples of our own research work that we have done for using some of these models and analysis. For example, I talked about flood vulnerability analysis. So in my state of West Bengal, there is a part where a lot of flood happens. And so we did, so what a very common method is, you take a lot of maps, base layers. So for example, elevation, slope, drainage density, then distance from roads, distance from levees and drainage networks. And we use AHP or fuzzy logic or frequency ratio machine learning algorithms, right? And we then model it together, and we come up with what is called the flood susceptibility map. And so we can create flood susceptibility maps like this. And then we can show which block or which district, which part of the panchayat has the most flood susceptibility, right? And then this is the DTM data set for that area. And using this, hello, is everything fine?
Yes, sir. Yes.
Sorry, I cannot hear you. Am I audible? Is it fine?
Yes, sir.
Yes, you are audible. Please continue.
Thank you.
Somewhat
So
interrupted.
this is the DEM dataset of the area. So this is how you create the HECRAS model. And we also have to back it up with field data, right? Because the cross sections we are taking from the 3D dataset, whether it actually matches the field cross sections or not, that you have to ascertain, because that is your range of error. You have to understand that while you're doing any model, that any model will have a degree of uncertainty. So you need to model and mention the uncertainty in your research papers also, or in your works also. And so this is the model that we created. You can create bridges also in the model. And then if you take the hydrograph data, you can put it into HECRAS and it will give you a simulation. Which parts of the area will be flooded, right? And then you can, so this is the output that we got, which parts will be flooded. And then you can correlate that with actual field photographs. Did that part really flood in that particular event? Or you can correlate that with the Google Earth images that, okay, these were the sediment plumes or the water plumes that came out where the embankment or the breach broke, right? So this is the kind of work that can be done. Then there is flood vulnerability analysis, where you take the socioeconomic parameters of different villages and you map them according to, say, literacy, access to the economic resources, and you find out which villages have the highest flood vulnerability. So if a flood takes place, which are the areas where you need to concentrate first, right, for giving the relief parameters. Then something that is very much ignored, because what happens is whenever flood takes place, people become very concerned. And as the water goes down, people think, okay, the situation is fine now. But when flood happens, what occurs is this. As flood happens, I'll just show you some images. So these are the pre-flood images, right? But after the flood, what you will see is that the waters will leave behind sand deposits. See, you can see the different sand deposits, the white patches, the sand deposits that are left by the flood. And once the water goes down, people think, okay, everything is fine now. The flood situation has gone. But these sand deposits that are left along the river bank, they create a lot of problem, because farmers, unless they remove these sand deposits, they are not able to do agriculture for the next few years. So we did a study where we saw how long these sand deposits stayed before they could be removed by the farmers and they could come back to some normal system of agriculture. So see, you can see from Google Earth, these are the sand deposit situations that arise, right? And so these are some of the field photographs that I'm showing you. And so you can see how the sand deposits are changing over time, right, in a particular area. So the area where we saw it, it took 9 years for all the sand deposits. So this is the sand deposit. The flood was in 2007, and finally they were all removed in 2013, 2014. Okay, so we could map the sand deposits and we could show which villages were the most affected. So by using multi-temporal high-resolution remote sensing data sets, Google Earth or other such data sets, you can do this kind of work. Then the flume I was talking about, we could model how the river would meander in the flume, and using that, see where the overflow is taking place, where the channel is breaking off and flooding a nearby area. We could also model, so this is the 3D models from it. So we could also create the most likely areas where the river will go and create sand splay deposits. Okay, so this becomes another kind of warning method that can be done. Then using remote sensing data sets, Professor Padmalal in Kerala, he has done a lot of work in sand mining mapping in India. So if you look at the sand mining situation in India from Google Earth images, I'll just show you some examples. Just a minute. Right. So see, this is a river channel that is there in 2016. Can you see the sand mining hollows that have been formed in the bed of the river? Right. So this has changed the water quality conditions. This has changed the flow conditions of the river. So by using high resolution Google Earth images, we can track, you can see again the sand hollows or sand holes that have been formed in the bed of the river or along the point bars in the river, say the small dams that have been made of sand dams, or trucks also you can see where they are going to try and collect the sands. So this is another kind of water resource or river ecosystem mapping that can be done using this particular high resolution images, right? Then I'll show you some other examples, other studies that we have done, not just for rivers, but if you go to glacial areas. In glacial areas also, this was done by my student at Leeds University. So what you can also do is, you can do GLOF modeling, GLOF, Glacial Lake Outburst Flood. So you can map the different glacial lakes that are there in different parts of the Himalayas. We did this in the Sikkim Himalayas. So you can map the different glacial lakes, and you can simulate the outflow of water from each lake. if there is a dam break, if there is a moraine dam break, all of us remember the Kedarnath flood that happened, the Kedarnath disaster that happened in 2013. So if similar, glacial lake recession takes place, right, and we can use different parameters like the size of the lake, the height of the moraine dam, if a river is connected with the lake or not. So if you're interested in this kind of work, that also is possible using good remote sensing data sets, and we can simulate if flooding takes place, then which areas along the river will be flooded. So these villages will be at risk along the rivers, right? So which parts, how far downstream will the flood wave propagate, right? So these kind of analysis can be done using different models and HECRAS and other such simulation systems, right? So which are the structures that can be at risk to such a GLOF event? This can be done very nicely, right? Then I'll show you some more studies. We have around half an hour. So I hope you're not bored. Is it all right so far? Hello? Hello? Participants, is it all right? Are you understanding? Yes? Okay, thank you. So, fine. So I'm sorry I cannot interact with you that much. That is the problem of online lectures. If we were face-to-face, this would be much better. Then from multi-temporal remote sensing data sets, you can do studies in a place like the Damodara Basin. And I'm showing you the Damodara Basin. Why? Because one of the largest and the first, possibly the first multi-purpose project that was taken up in India was the Damodar Valley Corporation, DVC, which was framed on the basis of the Tennessee Valley Authority in the US. So from 1940s onwards, we have had dams in the Damodar River, right? And so the changes that have occurred in the landscape as a result of such dams, the kind of reservoir sedimentation that has taken place as a result of this, say, 70 years or 78, almost 80 years of sedimentation behind the reservoir. This kind of analysis can be done from multi-temporal high-resolution image data sets. And you can see the villages at risk. We can map the different courses of the river at different times, say from 1969 all the way to 2014, we did this study. So you can see the river channel changes that will take place, shifting thalweg of the area, which parts are getting eroded, which parts are getting deposited. These are some of our field photographs where we did this, right? So what are the changes that are taking place in the topography, right? Which sites are more eroded, less eroded? And then what are the ancient paleo channels? Because this part of the Bengal Delta has a lot of paleo channels. So we could map the different paleo channels that is there. This has been done in different studies. And why are this paleo channel mapping very important? Because these paleo channels will be depressions in the topography. So this is where the flood water today will go and accumulate. If there is rainfall, if there is overtopping of the main river, this is where the flood water will go and accumulate in the paleo channels. You remember the Bihar Kosi flood in 2007 and 2008, where the entire river shifted, right, in August 2008. That was following one of its old paleo channels. So paleo channel mapping is very important, not only in flood situation, but also in normal situation where these are the repositories where surface water will be stored or where groundwater will be recharged. And you can then, if you put in a well, that becomes important for you. And this is important in Bengal Delta. Why especially? Because we have a lot of arsenic problem in the groundwater. So if you pull up groundwater from certain places in, say, Nadia, Murshidabad, these districts of West Bengal, southern West Bengal, then there is an arsenic issue that arises. But arsenic will never be there in surface water, right? That is not going to be contaminated. So if we can map good sites of surface water storage throughout the year, recharge throughout the year, and frame river water harvesting schemes using these remote sensing data sets, then you will really have a measure to alleviate the arsenic problem and improve human health in that particular area. Okay, so flood analysis can be done. Paleo channel analysis, flood analysis, this is in the Ajay River again. This kind of work can be done. Then something that is very common in using remote sensing data sets, especially from the hydrogeological perspective, where we take a lot of such data sets, then we overlay the maps together, we put again AHP or ANN, we run some algorithms, and we then demarcate suitable groundwater recharging sites, or we demarcate suitable check dam sites, suitable pond catchment sites. And since pond catchment analysis or lake ecosystem analysis has become important. Why? Imagine the lakes of Kashmir, Dal Lake, Wular Lake, or imagine the lakes in South India, Koleru, Eleru, Chilka Lake in Orissa. They all have a certain catchment from where the runoff goes into this particular lake or lagoon, right? So the landscape analysis of that catchment becomes very important, because if there is land use change within that catchment, if there is more amount of sediment that is now being run off, or more amount of pollutants that are being run off into the lake, the lake ecosystem will suffer. So we have seen, as a result of such land use changes, the ecosystems changing in Kashmir, the ecosystem changing in Koleru Lake, right, where a lot of eutrophication has taken place. A lot of the lake has become bogged down by bad vegetation communities, right, or invasive vegetation communities. This is one big area of work that can be done using remote sensing. And the CGWB and our different NIC, National Informatics Centers, they have made such detailed water resource management plans for different blocks across the country. You can download this. This is, I think, part of the Rajiv Gandhi Bhujal mission. So you can go to the website, Central Groundwater Board website, Rajiv Gandhi Bhujal mission. You can download such maps. They have a very, very detailed legend, and you can see which areas they have demarcated for water resources, where you can have pond recharge, where you can have check dams. Okay, so these are some of the maps that you can have a look at. Okay, what kind, where are the places where structures should be created, not created. Okay, so these are some of the outputs. This is a very, very common. You will find lots of papers on this. Say groundwater augmentation, use of the drastic model, use of the syntax model for estimating groundwater vulnerability. These are a lot of work that has been done using remote sensing and GIS datasets. Okay, so shallow irrigation, deep irrigation. Then say, for example, say this is a check dam. Okay, and behind the check dam, because desiltation has not happened, see, all the silt has got deposited, and now there is land over here. So there is no longer any place for the water to be stored. So this check dam has lost its utility. Right? This is in Purulia district. So we can monitor the reservoirs also using remote sensing multi-temporal datasets. Okay, so this is another work that I wanted to talk to you about, some insights. Then if you look at our CGWB website, they give you good groundwater data. And that groundwater data is given for 4 times a year. For example, you have February, then May, then I think August, and then November. And if you take these different data sets, you can make it into pre-monsoon period, monsoon period, immediately post-monsoon period, and then far away post-monsoon period. So you can use this data, plot these wells, and you can do the water table fluctuations that in the area from these different time period data, or monthly or 4 monthly data. You can do the water table fluctuations in an area. Right, so this kind of work can also be done. So you can show the areas of water table recharge, water table deficiencies over time. Okay, this is another example I wanted to give to you. Then a very, very crucial and new domain of work that has come up today, very, very crucial and new domain of work that has come up is your river ecosystem analysis, river health. Because see, we have had a lot of analysis or a lot of studies on the physical aspects of rivers or the physical aspects of ponds and coastal areas. But we need to now conserve our rivers. We need to protect our rivers so that their health is good, their ecosystem is good, so that we can continue to take the valuable services we can get from them. So riparian ecology assessment using remote sensing, that is a very, very emerging field in right now, very relevant field right now. And so this is a study that we did again in West Bengal. We studied a river. We looked at 54 sites along the river, and we use a Rosgian stream classification method where you can give a character, where you can characterize each channel segment of a river, right? And then we used the Behi. Behi looks at the bank erosion hazard index. Then we use the banks model. We use something called a river morph software. The river morph software looks specifically at river morphology and river meanders. So you can explore this software, right? Then we looked at something called a QBR. QBR is the quality of the riparian vegetation, that index. So we looked at this particular index. This is field based. Along with this is where the remote sensing comes in. We looked at something called the riparian strip quality. So what this does is it looks at the vegetation character from satellite images along the main rivers. And the logic is that if the river is in good health, then the vegetation along the river will also be in good health. So I will get a proxy of the river health and aquatic ecosystem using the vegetation along the river. Okay, so we looked at this. So these are these 4 5.8 meter images, and we have published this paper in the journal Ecological Indicators. I will share it with you. You can have a look through it, through the methods. And so we could characterize what was the RSQI values, and then inputting all these things together, we could show which branch of the river, which part of the river was in good condition, good health, poor health. Okay, and then along with it, we could add the water quality analysis. So we took the water quality analysis from the field, and then we did the water quality analysis, and we showed which part of the river was good, which part of the river was not so good. Okay, and now what advanced remote sensing also offers us now is it allows us to do water quality analysis from satellite images. Not all the parameters, you will of course need secondary data, but some parameters like your TSS, that is total suspended solids, then your total amount of chloroform, the temperature of the water, these can be done using satellite images, especially your Sentinel images and your Landsat 8 images, Landsat 8 OLI images. So this is a paper that we just published in Science of the Total Environment, where we show during the lockdown period, how was the Yamuna's water quality affected. Right? So I will share this paper with you. I'll show you some of the diagrams from it that we did. This is the Yamuna, right? And so these figures are based on actual collected water samples. This is provided by the Delhi Municipal Authority. But this is where our image analysis comes in. So there is a toolbox called the RBINS toolbox, which is specifically used for analyzing chlorophyll content, specifically used for analyzing the total suspended solids in the water column. So you can gauge this. So we could analyze the turbidity in the river. So this was before the lockdown, and this was after the lockdown. More blue means more clearer water. So as a result of the lockdown, the water had become much more clearer in the Yamuna River in Delhi. So you can do such very good analysis. You can see the suspended particulate, what is the concentration, the total turbidity. And these are very important parameters because high suspended particulate matter, high turbidity means the water is very, very brownish. There is less penetration of sunlight. Due to less penetration of sunlight, there will be less photosynthesis. There will be less amount of dissolved oxygen. And due to less amount of dissolved oxygen, the aquatic ecosystem will suffer, and BOD, biological oxygen demand, chemical oxygen demand will increase, and you will have eutrophication of the river channel. Okay, algal growth will become higher and higher. So these are some of the diagrams that we made for this particular work. Right, I'll show you some more diagrams. Right, we did some cluster analysis and other such analysis. So this is some change that can be done, and you can even do this from high resolution images. If I show you right at the end, see the Google Earth images that is there. Yeah. So this was the algal growth before the lockdown period or just after the lockdown period, and how the algal growth reduced because the water became much more clearer. Right. So this is these are some estimations that can be done directly for even ecosystem and water health using the remote sensing methods. And therefore, those of you who are interested, these are some of our works, but I'll show you now two PPTs made by other organizations. So one is made by the European Space Agency, and this is what they have done is by Eric Lilisov. What they have done is wetland change. So you have a lot of wetlands all across India, in South India, in my part of the country. And so wetland ecosystem assessment is very, very important. And there are today specialized tools, remote sensing tools, specialized machine learning algorithms that can be used to obtain good indices for wetlands. So see, these are the data sets that we can use for wetland mapping. If you go to the WWF India, that is World Wildlife Fund India website, you will see a lot of wetland mapping examples, right? Because a lot of flora and fauna depend on such wetland ecosystems. So you can use the range of satellite remote sensing. So this is how it is done. You obtain the seasonal remote sensing data. Today we have SAR data, and SAR is very important. Usually everyone still uses optical remote sensing, Landsat, Sentinel-2 data, right, which is optical. But if you learn microwave remote sensing, and I guess you have some lectures on microwave remote sensing, you can use the SAR data, synthetic aperture radar data. And why is this important? Because SAR is cloud penetrative. The X band and the L band radar, they are cloud penetrative. Because they are cloud penetrative, they can look at the land surface in India during the most crucial part of the year, that is during the monsoon. During the monsoon, what you will see is you have dense cloud cover. Optical remote sensing will not serve its utility. But using the SAR data, you can look through the clouds, you can look at the extent of the inundation, you can look at the extent of biomass change in the wetlands. And so this becomes very, very important. And you can integrate this optical and SAR data with other DEM data that we were discussing and go on and do such work. So these are the various data sources. Please explore these further. I cannot cover everything within this short time, but please have a look at such data sources. These are the websites. I'll send you the presentations if you want. And so please explore these further. So wetland growth and wetland reduction, how the wetland grows seasonally, and that increases the soil moisture, that increases the wet area coverage. And we have special indices like NDWI, Normalized Difference Water Index, or the MNDWI, Mean Normalized Difference Water Index, to gauge such parameters, and then how that affects the local ecosystem. So we can use Landsat, Polsar, that is the SAR data we can use. Right? We can use principal component analysis on the SAR data to reduce the bands, so we can get a clearer signature. We can use hyperspectral data. We can even use SRTM or LiDAR data for this. Okay, and so then we can integrate the data and do very good mapping of wetlands all across the world. So this is something that is very much important. Okay, and this is I'll share this presentation with you. Very importantly, in South India and in West Bengal, we have wetlands, rather mangrove areas. And so mangrove areas need to be imaged. And so their mangrove areas are today very important in focus. Why? Because they are the first protection against coastal storm surges, right? And there we are using a lot of different techniques to monitor mangroves, to preserve mangroves, right? This is going on. And in that relation, something new has come up, using of drones in agriculture, using of drones for water management. So I'll share this article with you. It came out in the MDPI journal Water. So how drones are being used in water resource analysis and management, right? This article describes that briefly. There are many other such examples where drones are being used to look at water resources, map water resources during, for example, map water structures, engineering structures, map the different extents during floods. And also I'll give you an example in Burma. In Myanmar, they are using drones to plant mangroves. What they are doing is they're fitting a gun, shooting gun below a drone. They are putting mangrove seeds inside that gun. And as the drone goes over, I'll just show you the website so you will have a clearer idea. Mangrove plantation drone Myanmar, right? I'll just show you the websites. So, these are some of the news articles if you follow. So if you are interested in UAV, this is one area where I am very interested to work in with any of you. So they are planting mangroves. Why? Because these are in inaccessible areas. If you fit the seeds of the mangroves plants in the pod below the drone, now it is going. The mangrove soils are clay and mud. It's very soft. They are shooting the seeds. The seeds are being embedded inside, say 30 centimeters below the soil, and then they are sprouting and coming up, and the mangroves are being, saved. So this is a way that we can really conserve our coastal resources, and we can really, improve the habitat quality of these areas. So again, remote sensing, drone-based analysis is becoming very, very important today. The last presentation I'll show you here has to do with how the use of remote sensing and for water resource mapping contributes to the Sustainable Development Goals, the SDGs, right? So these are the areas where we can use Sentinel data. We can do it for urban forest water quality analysis, flood water body analysis. So if you learn these things, you are not only contributing to in your own research field, you're also contributing to the Sustainable Development Goals. Sustainable Goal number 6, wetland mapping, soil moisture mapping, right? Then mapping chlorophyll, and we map a lot of chlorophyll. Why? Because on the extent of chlorophyll depends on the fish stock, the phytoplankton. On basis of that will depend the amount of fishing that can take place. So you're looking at the fishing economy in a particular area by mapping the chlorophyll index. Also, by mapping chlorophyll, you are looking at algal blooms, harmful algal blooms, which are an indicator of the eutrophication or the increase in the harmful chemicals in the water that will arise in a certain place. Okay, so these are some of the mappings, case studies of water quality monitoring that has been done in Malaysia, in Brunei, using different water quality indices and wetland mapping. So this is part of the Sustainable Development Goals, right? So this is how we do. We take the data, we produce the maps, we judge the quality, We see how fish species are being affected through field surveys. Then we can disseminate that information to the fishing industry. So you have a direct economic impact of your research. So this becomes very, very important. You can see the website for more details, right? And so because I was saying that this area has become very, very specialized, right? Today, by SAR data, Sentinel-1 data, we can even track the changes in the small islands, right? We can even track the changes in the small islands in the estuaries, how they are being eroded and deposited. And this study was done on Bhashan Chor. Bhashan Chor is in Bangladesh. And the reason why this was so important for doing on Bhashan Chor, because this is one of the main settlement sites for the Rohingya communities. The Rohingya communities who are being, this is what the abstract says. The Rohingya communities who have been forced to leave their homes in Myanmar, they are settling on this Bhashan Chor. So to judge the suitability of the refugee camps, we can even use remote sensing for these purposes, right? So that's a very hugely applicable area. So if you want to know more about this for river health mapping, now there are river corridor analysis that is coming up. For example, Professor Kirsty Friars in New Zealand, they are doing what is called river geomorphic sensitivity. So mapping the various sensitivity along the different stream corridors and river channels. And she has coordinated with the government departments in New Zealand and Australia, and those departments are producing such river corridor maps on their websites to show which rivers are in good health, which rivers are not in good health. So please have a look at her papers and her research, and you will gain a lot from those aspects also. All right. Now, I told you that this is a very, very specialized field right now. A book that is directly related to this would be, just a minute, please. I'll just find out. Yeah. So this is one book you can have a look at. Remote Sensing of Water Resources, Disasters and Urban Studies, Handbook number 3. This book is available online. It is, or you can purchase from CRC Press. You can get the ebook. So this will give you some examples of more water resources studies that are there. Then you can have a look at one of my favorite textbooks, Fluvial Remote Sensing for Science and Management. This is a book that is entirely devoted to remote sensing of fluvial areas, remote sensing of ponds and other such ecosystems. So please have a look at this book, right? And then I told you that your modelings, different modeling methods. This is another older book that is there, Remote Sensing Approaches in Hydrology and Water Management. This book you can have a look at. This is brought out by Springer. You can have a look at. This was in the year 2000, so slightly older. And I told you that this domain has become very, very specialized, right? So there are 4 volumes. I'll just show you the 4 volumes quickly. Just a minute. Let them open. Right. 4 modeling volumes that have come up. So the first one is, this is called Floods in a Changing Climate, right? This is called Floods in a Changing Climate. The first volume is called Extreme Precipitation. See, just the analysis of the rainfall, just the model. So if you go inside this, you will get lots of equations and models and all other things, how to just model the different rainforms. So this is a book that you can look at. Then the next one is by P.P. Majumdar. I told you to refer to his works. Though taking after analysis of the rainfall, then the analysis of the hydrologic modeling. Hydrologic modeling means the rainfall conversion into runoff. So the rainfall runoff modeling. After that, the next part is the inundation modeling. That means a flood modeling, right? And the last part is the flood risk assessment. So that is the risk modeling. So see how specialized the modeling domain has become in the water resources sector using remote sensing and GIS datasets. So please have a look at these 4 volumes. The more you read this, the more you will gain. I'm always happy to collaborate and work with any of you. And I will learn also a lot in the process, I'm sure, right? Then finally, I will end with showing, because we're running out of time, I'll just show you some different websites. So this is the Nptel website. Just bear with me. I'll just show you some websites. So this is the Nptel website. Nptel is a repository of free lectures that are online, made by the IITs and other such institutions. This is for water resource engineering. So you can avail of their researches online, and they'll have remote sensing and other aspects of the hydrological sciences. Okay, so you can look at the Nptel website. That's a good domain to look at. Then you will get other such courses on what is called e-courses online, right? Remote sensing and water management in India. You will get other such aspects on this particular website. I'll share the links with you, right? I'll share the links with all participants. Then there's a new startup company. This is a startup company that came out of IIT Kanpur a few years ago, and they are doing something very novel. At the start of the lecture, I told you that India is a data sparse country, right? We are a data deficient country. So they are creating some very nice instruments which are of very low cost and which can be used for water resource monitoring. Say the water level in rivers, water level in reservoirs, right? And you will get directly the data on your mobile. Every 15 minutes, they will do real-time monitoring. And so if you want to talk with this company, they are doing a lot of good work, and you can have a look at their data products, Krishnam. You can have a look at their data products, how they are monitoring the different lakes and reservoirs. Okay, it's a very, very simple system. They are basically fixing, let's say, a sensor on underneath a bridge, and that bridge is constant. That sensor is recording the level of the water, and that water data is coming to a nearby cellular tower, and from the cellular tower, it is coming to your mobile phone directly. So every 15 minutes, you are able to get a very rapid monitoring of what is going on, right? And they are doing a lot of good work. So this is one startup company in India who are looking at this. Then one of the main repositories of data, I showed you the India RIS website earlier on, but we have our Bhuvan. This is our own digital globe. And if you go there, you will see examples like Clean Ganga, flood warning, flood vulnerability, ocean services, disaster management services. So this has a lot of, so if you click on water, then you will get a lot of water resources issues related data sets and remote sensing data products, which you can go, you will get hydrological data products, vector shape files are available, right? So if I just show you the hydrological data products, then you will have a wide range. See, hydrological fluxes. That means the changes in runoff taking place across India at different times of the year. You can download this. So this is for 22nd September. If I give a date, let's say 6 September, I will get the maps for that time. So you can do a very nice directly temporal analysis based on the data set that you can do surface runoff, soil moisture assessment, evapotranspiration assessment, and you can download the data set. After you log in, you can download and obtain the data set that is there, right? So this website is very good. You can please have a look at the Bhuvan website. I'm sure many of you have already seen the Bhuvan website that is there. Then this is the CGWB, Ministry of Drinking Water. So this is where you get very detailed groundwater maps. I was talking about the Rajiv Gandhi Bhujal mission. So if you accept their disclaimer and if you go to this website, then you will get very detailed groundwater maps which you can obtain for the country, for your area of work, and you will gain a lot from these data sets, right? So a lot of data is available. Often a lot of time goes in us trying to search where is the data. So that is something that has now been done away with. Then JPL is Jet Propulsion Laboratory in NASA. They have started a program called Imaging Surface Water from Space, SWOT, Surface Water and Ocean Topography from Space. So this is their website. If you go over there, you will have a lot of data downloads and how they are doing this work, what role remote sensing is playing in this. And you can read up. A lot of resources are there, documents and directory and all these things. You can download these, right? So you will have a lot of data sets and different technical documents that is there. Then we have something called riverscapes, because I was talking about river corridor mapping, right? I was talking about river corridor mapping that is going on. So if I go to the Riverscapes Consortium, there are specialized tools for mapping different river corridors, mapping different geomorphic units within river corridors. So you will get a lot of models from here. You see RC tools are there. You'll get a lot of tools for mapping the river corridors. And I work with this. So if somebody wants to work with me, collaborate, more than welcome, right? I'm sure we will all benefit a lot in this process. Okay. Then if you go to the CSDMS website, this is the modeling community based on Python and MATLAB modeling and R modeling, which is there at the University of Colorado. Let's see if the site can be reached, or I'll open another site. Am I audible? Yes, no?
Yes, sir. Audible.
Okay, fine. So if you go to the CSDMS website site in University of Colorado, they have a lot of models, hydrological models that are there. You can download them. The site is not opening sadly at the moment. Let's see if it comes now. Anyhow, if you go to the NCAR website, see there are a lot of hydrological data sets remote sensing data sets that are there. So air temperature, humidity, sea indices, precipitation over Asia. These are almost daily data sets. You can download this and you can use this in your work. All right. Just remember the name CSDMS. The website will open later on. And there is a Hydrosheds program. You can look at that. Then something new that has come up called Blue Earth. Blue Earth is the website that has come up, which looks into large-scale gridded hydrological data. So if you agree with the data consents and see, it will give you water level, surge height, tide data. So if I say, let's say I want to see present water level data across the world, right? Let's see if I want to see this data set. So all across the world, it will give me at this current moment, it will give me the different water levels in the oceans. See, that is coming, right? Or if I switch this off, if I want to see discharge data at this moment, it will give me the discharge data for the different rivers of the world for a certain date. And I can download this data and I can use this gridded data and I can go ahead. So even if, you know, the data from the CWC is restricted for parts of our country, if you are working at coarser resolutions, you can use such gridded data products and you can go ahead and do your work, right? So these are some of the things that I basically wanted to talk about in this lecture. Let me just see if I have any other things to show you. This is another book, right? So these are some of the main things that I wanted to talk about. So if you have any questions, I'm happy to take those now. And I hope this has been a little bit useful for you. And it's been my pleasure also. I apologize for the interruptions with the internet network, right? So this is what I wanted to say. Right? So I hope it's useful.
Yes,
right.
sir, of course. Participant, if you have any questions.
And I hope you have enjoyed the lecture also.
Sure, sir, sure.
Yes, so if there are any questions, I can, you know, you can either type in your questions and I can answer. I can read the questions and I can answer them here. Or what I'll do is, instead of sending it to individual emails, I will send some of the stuff that I'm showing to the organizers, right? And you can get it from them directly because that will be much more easier. Nobody will miss out. So if you have any questions, you can type in, right? So can we calculate TSS and turbidity using Landsat 8 or Sentinel data? Of course, you can do that. If you look at, let me just show you the, this is the paper that we did. I will share the paper with you then. This is a paper that we brought out on the Yamuna, and here we have calculated the turbidity using the Landsat 8 data sets, and you can also use the Sentinel-2 data. You cannot use Sentinel-1. The coefficients are not there. But you can use the Sentinel-2 data set to get TSS and turbidity. But I must warn you that it is very, very sensitive. And so you must have some field data in which you can compare the error range that you are getting. Because if you present just directly derived from the remote sensing images, maybe a good journal will not accept. Okay. So can you type in the other question? So I will share the paper with you. You can follow that and you will get the method over there. Right.
Hello, sir.
Hello, Sanjeev.
Sir, what the use of toposheet in georeferencing? Can you define me, sir?
Okay, toposheet. See, toposheets are the main.
Yes.
Yeah, correct.
Geocoding and georeferencing, na? We use the toposheet in geocoding and georeferencing also, na?
Yes. So toposheets will give you the very accurate coordinates because these are ground survey points. So if you scan your toposheets at high resolution, the latitude, longitude you can extract from them is very, very important, right? Because that is actual ground survey points. And it is based on those toposheets that we create our digital terrain models and use those to rectify our satellite images, right? So that becomes important. Not only that, today we have altimetry data sets, satellite altimetry data sets that are also very accurate. Those can be used, but our toposheets are the main primary database which we depend on in India, made as part of the Great Trigonometrical Survey by George Everest and William Lambton. Also, you will realize that remote sensing data sets are available only from 1970s onward. In the 1960s and 50s, you had the corona photographs. Before that, you had some air photographs from old planes. But if you want to go back 100 years, 1910, 1920, then you have to depend on the topo sheets, right? If you want to see 100-year change or 150-year change in river patterns or in reservoirs areas, right, or coastal belts, you only have to depend on the topo sheets. So you will get the old topo sheets from the British Museum or from Survey of India. Recently, Survey of India started the SOI Nakshe website. Let me just show you. Okay, SOI Nakshe website is there. So you can, if you go to the SOI Nakshe, I'll just show you the SOI Nakshe website. Just a minute. Right. So if you go to the SOI Nakshe website and you have to log in, no, not this, sorry. Yeah. If you go to the SOI Nakshe website, you will have to log in with your Aadhaar, and you can download topo sheets from here. This is the Survey of India website. You can download topo sheets from here. They are giving this now free if the topo sheet is there for the entire country, right? Okay. Next, okay, please.
Sir. Thank you, sir.
Thank you. From where can we get satellite image of North Bengal area free of cost for different time period? You will get from the USGS repository, USGS Earth Explorer. Then Sentinel images you will get from the ESA repository, European Space Agency repository. Just search these two terms, USGS Earth Explorer and ESA Sentinel. You'll get data sets from there. All right. Then which model is more suitable to identify groundwater potential zone? There are different models, right? If you want to look at vulnerability, there is the drastic model, syntax model that is used in Italy and other parts of the world. You'll find lots of papers on drastic model use, DRASTIC. Okay, then you will have something called the ModFlow, ModFlow. ModFlow is a software that looks specially at groundwater modeling, groundwater pollutant modeling. Okay, then you can use groundwater fluctuations. If you look at the, I think, data tools that are there in the RockPlot, RockPlot, in the RockPlot suite, or the Rockware, sorry, in the Rockware suite, software suite, there are special data tools to model groundwater areas. Okay, so those and using borehole logs, drilled borehole logs, which engineers will do for tube well mapping. Okay, that you can do. Okay. Then what necessitates the changes in rivers before and after lockdown? What we saw in the Yamuna study, and there have been 1 or 2 more studies, is that because the industries were shut down, the release of the industrial effluents were less. So as a result of the less industrial effluents going into the river, what happened is the river turbidity declined. And as the river turbidity became lesser and lesser, the river water became clearer. I'll share the Yamuna article we did with you. You can read the effects on the Yamuna in Delhi. Okay, in near urban areas, this effect was not so much because we were still in our homes, we were still using the dirty water in our kitchens and in our bathrooms, and we were, so sewage from urban areas was still in the same amount, but the industrial effluent amount had come down. Okay, then what is difference between DEM and slope map? See, DEM is just a data set. Just the terrain data is the DEM, which shows the heights. Using that, we can extract the slope map by asking the softwares to plot the gradients between the different pixels and the 2 points. So DEM is the base data, slope is the derived data from the DEM. Can we demarcate channel morphology using Landsat Sentinel? Of course you can do that, but remember Landsat is 30-meter data set. Landsat 8 high resolution or Landsat 7 band 8 will be your 15-meter data set, but it's still a little coarse resolution. You can do it from Google Earth. If you want long term, then of course you have to go for Landsat. Sentinel is 10-meter data, so that is a much better higher resolution data. Of course, you can demarcate channel morphology from that. Please look at the papers by Gary Beerley and Christy Friars, who have used these data sets to demarcate channel morphology. They have done a lot of good work. I have done some work in this domain. If you want, I will share with you. Okay. Yeah, please do get in touch with me. Amshuddin from Nigeria, I'll be happy to talk with you. And from where can the other questions, if I, are there any other questions? Okay, I'll just scroll down. Right, the other questions that are there is, which satellite sensor records CO2 emissions? CO2 emissions are recorded. You will also have methane. This data is available for free. A lot of studies have been done using the impact on the air quality during the lockdown. So this aerosol data, these methane emissions data, these are available. Go to the NASA websites and you ask for gridded air quality image data, and you will get such data sets over there. Okay, so these are of course available, and the Aqua and Terra and other such satellites that are there, I may be wrong, though those will be available. Okay, so is there any specific algorithm for a specific kind of terrain? See, other than D8, see, that is why I told you should take the DEM data you have, run it through the different kinds of algorithms, right? Look at something called Geospatial Whitebox. Geospatial Whitebox is a small software. It's a free software which allows us to look at the different other flow routing methods other than the D8, and then you can you can judge which is best for your area, for your terrain. Usually D8 gives good values, everybody uses it, but you can, for sake of curiosity, you can look at the other data sets, and maybe that will benefit you also. You told some groundwater data. Yeah, groundwater data you will get date-wise. If you go to the CGWB website, if you go to the India RIS website that I showed you, WRIS, there is a groundwater module. For the last, I think, 30 years, they will give you data every 4 months. 4 times a year, they will give you data for different bore wells. Okay. Is air quality data available for free? Of course it is. You can, if you just type air quality data India, you can go to the National Air Quality Portal, and it is already, the calculations are done. You can directly get the data product from them for your area, and you can do the mapping. Okay, you can get it for individual stations and do your own calculations, or the air quality index is also calculated and kept on the website, and you can directly take it from there. Okay, and you will be able to see the aerosol changes, PM 2.5, PM 10. Okay, these changes you will be able to track in the atmosphere, right? So any other questions? Yes, so stations where air quality data is not there, there you can use the gridded atmospheric data, because gridded atmospheric data is available for the whole world. Okay, so you can use the gridded atmospheric data, and you can model air quality throughout the entire world. A lot of studies have been done during the lockdown period for this. If you search online, you will get a lot of such references. Is there any way to generate SAR, DEM from SAR? There is no easy way. You have to use something called SAR interferometry. You have to unwrap the data. I don't know this technique so well. It's a difficult technique because you need good ground correction points, and you need good checks. So there are specialized software suites, for example, the ESA toolbox, Snap toolbox, that allows some processing to be done. Then there is the ENVI NV software that allows your SAR processing. In fact, NV is also something very good because the NV software affords the best your atmospheric correction data sets, right? Along with this, there is a new software now available called the Orfeo toolbox, ORFEO. The Orfeo toolbox, it's a lot of Python codes, which Python codes you can run in QGIS also. And these Orfeo toolbox can do very nice atmospheric correction for you. Ideally, you should do atmospheric correction, then only utilize the satellite images. You should not utilize satellite images directly to obtain NDVI and NDWI. You should first change the DN value to the radians, then to the at satellite radians, then to the atmospheric correction, then only do the NDVI processing. All right, so this is very, very important. Right, if there are any more questions.
I think
some DTM data source. DTM is not available for free in India, but if you look at USGS for England, US, you can have the DTM data sets from there. I will share my email with you. You can write in to me with any queries, and I will be happy to answer. Right?
Shall we conclude, sir?
Yes, sir. Let us conclude.
Okay.
I hope it has been useful.
Sure, sir. Sure, sir. On behalf of our Department of Civil Engineering, we are really thank you for accepting our invitation and come over here and presenting a very informative and interesting topic. Really happy, and thank you very much, sir, once again. Now the session is over. We will meet at 2 o'clock.
Okay, sir. Thank you so much for having me. Thank you, sir, for having me.
Okay, sir. Thank you. Thank you. Before leaving the room, all the participants are requested to attend the feedback link. Thank you.